Hello, this lesson is an introduction to harmonic motion. Now when we're dealing with harmonic motion, we have a spring, which is attached to something that doesn't move, so in this case a wall. And then on the other end of the spring, we have some kind of mass attached to it. Now we say that the spring has a constant, which is called K. And when we're writing out an equation for the sum of the forces, when dealing with this, so we'll say that the sum of all of the forces is equal to negative our spring constant, negative K, multiplied by x minus x0. Where x0 is the point at which our spring is limp. It's not being stretched and it's not being compressed. So it has no forces acting on it. That's our x0, and our x is our displacement. So our distance pulled from a certain point of reference. And this is of course going to be equal to our mass multiplied by acceleration. Now because we're dealing with, over here we have our variable x, which represents our displacement, so we're going to use the second derivative of our x, x double dot, and this is our acceleration. You'll see why we write it like this. So this equation is the equation for harmonic motion. It's very important. Please write this down. Another name for this equation, or the type of this equation, is that it's an equation of motion. So equation of motion. Now, an equation of motion is any equation that has the variables of acceleration, so here we have x double dot, that's acceleration, or velocity, or displacement, x is displacement. And it can also have two of them, or if you find something with three of them, it doesn't matter. Those are equations of motion, and this equation describes harmonic motion. So if we have a harmonic system, this equation will describe its starting position, its velocity, and so on and so forth. Another useful trait of this equation is that if you get a question in which you're asked to prove that some system is working with harmonic motion, if you can get the equation of your system into this type of format, then you can know that the system is in harmonic motion. So our equation over here has to be in this exact format. So what does that mean? That means that number one, this negative must always be here. Always, always, always. Number two, that means that our k and our m are positive constants. So this is a const. And it's a positive, and also this is also a constant, and it's positive, and we must always have our x0 here. Now our x0 can be positive or negative, but it's also a constant. But this can be positive or negative. It's the only difference. And it must always look exactly like this. So you'll notice that we have here our x, and here we have an x double dot. So that means that this is a differential equation, and the answer to this differential equation, which if you want you can solve on your own, is going to be our x as a function of t, so our displacement as a function of time, is going to be equal to a cosine of omega, angular velocity, multiplied by t, plus phi, and then plus x0. Now a lot of teachers or a lot of professors will omit this x0. I think that it makes it more clear and it's a more accurate answer, so you can write it if you wish. Now this equation is called the general solution to this differential equation. So this is the answer. And now let's take a look at what this means. So we can see that our variable is t, so we have a t over here and a t over here. This is the variable of the equation. And now we have all sorts of constants in here. We have our a, we have our omega, we have our phi, and we have our x0. Okay, so now what we're going to do is we're going to take a look at what each of these values means. So let's deal first with our x0. Now our x0, over here we said that this is where our spring, okay, doesn't have any forces acting on it, okay, it means it's limp. So, but here when we're saying it, we're speaking about the point of equilibrium. Okay, where the forces are balanced. So it's not necessarily limp, but the forces are balanced. So point of equilibrium.